Okay, so today what I want to do is give an important application of convolution, and in doing so, we'll run into a bunch of examples, some of which will show up later, some of which I sort of give, and maybe you may see or have already seen them in different contexts. And everything is connected to the notion of approximation. And regularization. Using convolution. Okay. All right. So the idea is we want to take some space of signals and possibly spaces of distributions and approximate them with elements of some other space of signals or distributions. And correspondingly, you want to take some kind of irregular or space of irregular functions, and by irregular I mean not continuous or differentiable or twice differentiable or however, and convert them with, approximate them with signals which are regular. Okay, and generally the regularity of the approximations that we want to talk about here is infinitely differential. So you want to convert, regularize a discontinuous function with an infinitely differentiable one. Okay, and convolution provides you with a device for doing that. Okay, so first thing we'll talk about is the notion of approximate identities. Okay, and so approximate identities are sequences of signals with important properties that follow from their definition, but first let's give their definition. So there's various, well, we're really two kinds of approximate identities we're going to talk about. The first we'll call aperiodic. Okay, and so these are signals defined on all of R that are not periodic, because we're also going to talk about periodic approximate identities as well. Okay, so that's the context here. Okay, so definition and approximate identity on R is a sequence uj, and I'm going to ask that the sequence be in L1. And it has to have some properties. Okay, so first, the integrals should all be equal to 1. And you can relax this a little bit by just sort of requiring that the limit as j goes to infinity of the integral should be 1, but then you can normalize them all to be 1 anyway. Okay, and an important condition, and one which doesn't hold in some cases you'd like it to, would be that there's a uniform L1 bound on the L1 norms of all of these things. Okay, so there exists an M positive such that the L1 norm of all of these UJs is less than or equal to M for every J. Okay, so it's very important because you can imagine where this might show up. It's going to show up. It's somewhere embedded inside of all of this is going to be the dominated convergence there. Okay, so but I'm not going to be proving anything. I'm going to be covering a lot of material today without proof, and the proofs are not. I guess I would say standard in some way, but one should definitely look at the proofs before accepting these facts I'm giving. Okay, and the other thing has to do with the tails of the functions in the sequence UJ. Okay. And so you choose an alpha, and you require that the integral outside the compact interval of length 2 alpha around 0, okay, of the L1 norm goes to 0 as J goes to infinity. Okay. All right, so the tails of these things, by which I mean the signals outside any arbitrary compact interval around 0, or for that matter, any compact interval, that the tails should go to 0 in the L1 norm. Okay. All right, so that's what an approximate identity is. Now, why are these called approximate identities? Well, they're called approximate identities because what we're going to do, oops, is we're going to take F in some space of signals, and the exact statement of what's true depends on exactly the space of signals. Okay, so we take some space of F in some space of signals, and then show that the convolution of F with the terms in the approximate identity converges to F in some way. Okay. So that's the general approach here, and the precise nature of the statements that you can make depends on the space, and it depends on the convergence that you're that you get from the kind of approximating sequence. Okay, so the idea is you use these UJs when you convolve them with F to approximate F. Okay, so let's look at the various kinds of approximation that you get. Okay. All right, so what I want to do is sort of write these all down together in one list. Okay, so basically identifying the space and the kind of convergence. All right. All right, so the first situation that we're going to consider is F in LP. And here, P is from 1 to infinity. Okay, and in this case, what we get is that F involved with the approximated identity uh, converges to F in LP. Okay, so that means in the P norm. All right, so that's one mode of convergence. And it's kind of the best that you can expect if F is in LP. All right. What about preservation of continuity? Okay, so let's say that F is continuous and bounded. All right. Then what kind of convergence do you get? Right. So what you get is this kind of convergence. You get that F convolved with uj restricted to K. So K is going to be any compact set. Converges uniformly to F restricted to K. Okay, so what this means is you get uniform convergence on any compact set. All right. And so this isn't quite as good as you would like. You would like to get a uniform convergence on not just on compact sets, but uniform convergence on all of R. But the reason you don't get that, it turns out, is that being C0 bounded is not enough. What you actually need is not just continuous functions, but you need uniformly continuous functions. And then if you have uniform uniform continuity of F, then you get uniform convergence on all of R. So let's state that. Okay, so let me denote uniformly convergent functions by C0 uniform, okay, but I still need them to be bounded. Okay, so this means uniformly continuous. Okay, so if F is continuous, uniformly continuous and bounded, then you get the thing that you expected to get, or that you maybe hoped for. Okay. All right. All right, so it's interesting to see in the proof here just how it is that uniform convergence arises to give you the statement. So there's things here that are worth exploring that we're not going to explore. All right. And then the final kind of convergence statement that we're going to get for approximate identities is a kind of pointwise convergence. Okay, so we're going to take F to be in L infinity. You need to put some conditions on F to ensure that the convolution exists. Okay, so if you look back at our conditions for convolvability, you'll see that UJs being in L1 combined with these conditions is enough to guarantee convolvability of UJ and F. Okay. All right, so in this case, we're talking about pointwise convergence. So f is in L infinity, and you're going to fix some t naught, and you're going to require that f plus at t naught, which is going to be the limit, as t. Okay, so f plus means we're going to take the limit of the values of f as t approaches t naught from the right. Okay, so t will be descending down to t naught, f of t. Okay, and f minus of t naught is the limit from the left. Okay, so these limits exist. Right, and so, for example, if f plus is equal to f minus, then this implies the continuity of f at t naught. But you may not be continuous, but you'll sort of be continuous from the right and continuous from the left. Okay. All right, so if both of these statements are true, then, okay, f star u j j converges pointwise at t naught to f. Okay, and this means just exactly that the numerical sequence, when you evaluate these at t naught, gives you f of t naught. Okay. All right, good. So what you see is that this class of properties for a sequence, and you can see why these are called approximate identities, because you get a sequence which is approximately the identity, so it converts f into f. Okay, and so the idea is you want to choose the UJs in a specific way, so that these approximating functions have desirable properties. That's the idea. Because here we haven't really made very many assumptions on what the UJs are, and so in fact. So let's maybe look at examples of approximate identities. Okay. So if we take just a single f in L1, sorry, not f, but I'm calling this u. Right, and I'm going to ask that the integral over r u of t dt be equal to 1. Okay, then the sequence uj given by uj of t is j u of jt, okay, is an approximate identity. All right. Okay. So the idea here is one we've seen before. Okay. The idea here, so this u here is just in L1, and it has a finite integral, and if it has a finite integral, then you can normalize it to be 1. Okay. All right, so certainly, if it's in L1, then it'll have a finite integral because it'll have a finite absolute value, and so really, just anything in L1 here suffices after some suitable normalization. Okay. So these things can be pretty irregular looking, but I'm going to draw it like it's regular. Okay, and so then the idea is, let's say that one is U, okay, and that's going to be U1, all right, and then I'm going to amplify by J, and I'm going to dilate time by J. And if you think about the way that works, is that you you take your signal and and you kind of do something like this to it. You get the same shape of signal, but it becomes more concentrated around 0. Okay. Right, so we've seen this kind of behavior when we talked about distributions. We had this sequence of signals which looked like this, that we used as our input to some, or the right-hand side for some differential equation, to motivate the idea of distributions. And then we saw that this sequence converged in distributions to the Dirac distribution. Okay, so the idea here is rather the same, and in fact, you get convergence of okay, that you get convergence of so all right, so I'm stumbling around to say something here. And so you almost, so what you'd like to say is you'd like to say that if you have an approximate identity here, that converges in distributions to the Dirac distribution. That's almost true. You need an additional condition, which is a little bit stronger than that one, in order to ensure that that the sequence UJ converges to the Dirac distribution. But you can see the idea there. Okay, all right. So this gives us a way of building a large class of approximate identities. Just take any U and L1. Okay, so but I do want to look at specific examples because these are interesting in and of themselves. All right, so really, in some sense, what I'm going to be doing is, writing down functions in L1, but I nonetheless want to say something about them. Okay, because these are important objects in their own right. Okay, so the first one we're going to look at is what's called the Poisson kernel. Okay, and the Poisson kernel is a family of functions, and it's going to be defined like this. Okay, and here omega is some positive parameter. Okay, so you can verify that this that this thing is in L1. Okay, by so this is first of all, it's more than in L1. It actually satisfies this condition. Okay, so let's maybe look at how this guy behaves. And so this is a kernel which doesn't die off at infinity very quickly, right? It does it quickly enough to be in L1, but not incredibly quickly. But basically, it's a function that's behavior looks something like this as you plot it. So this is as omega gets larger, it tends to do this. Okay, so that's as omega increases like that. Okay. All right. So you can check that the integral over r p omega of t dt is equal to 1. Okay. So, you have to do that integral, right? Okay, so let's also notice that all right, so because so what we're going to do is we're going to consider that formula. Okay. So notice that P, so the interesting thing that happens here is that this formula, when you stick in this particular Poisson kernel, because of the way that it depends on the parameter omega and the way that it depends on t, you get a specific identity here, and that identity is p j omega of t is j p omega of jt. Okay. And so the point is that so remember that this thing here is exactly this relationship here. And so these are the, given a p omega satisfying condition like this, we know that the sequence defined like so will be an approximate identity. And this is true for every omega. All right. And so, for example, you could take omega equals 1 and define a sequence pj omega. And essentially what that serves to do is you replace omega with j. Okay, so the point of that is that thus the sequence pj, okay, so when I write pj, I mean p sub omega with omega equals j, is an approximate identity. Okay, and so notice that pj, of course, is 1 over pi j over 1 plus j squared t squared. Okay, so that's one way of building a sequence like this. But like I said, you can do this for any omega. I've just fixed omega to be 1 when writing it like so. Okay, all right, good. And so there's another and very interesting way of using the Poisson kernel. So let's now think of omega not as being a parameter, okay, but as being a variable itself. So let's think of p as being a function of omega and t. Okay, and what I want to do instead of using omega is I want to replace omega with 1 over omega. Okay, and so what this does is this kind of this means that so in this version, when you think of that formula, the idea here is that you're interested in the behavior as omega goes to infinity, right? As omega goes to infinity, these things get this focusing behavior at 0. All right, but by changing omega with 1 over omega, then in this new parameter 1 over omega, it says this new parameter goes to 0, that things become interesting. Okay, so let me write down what I just said. Okay, so now define, okay, P of X and Y, okay, by P, and like I said, I'm going to replace omega with 1 over omega, and so the role of omega here is going to be played by X, and so this is P of 1 over X, okay, so that's our omega, of Y, okay, and this, if you do the substitutions, is 1 over pi X over X squared plus Y squared, okay? So now the point is you get a function of 2 variables, and the role as omega goes to infinity here is replaced by X going to 0, all right? And so if you think about what's happening there, okay, so here's X and Y, all right? And so what we're going to do here is we're going to think of X and Y as being the real and imaginary parts in the complex plane. And then, like I say, as omega goes to infinity, X goes to 0. And so I'm coming in, approaching the imaginary axis, and X is positive here. You know, it doesn't have to be positive for that formula to make sense. Well, I guess it does if you want it to hold for every Y, because if X is 0 and Y is 0, then you have something to think about. But for positive X, the idea is that you're looking at functions of Y, okay? So functions that are defined like so, all right? So then if you have some functions, let's say, that are defined on the complex plane, okay? So let's say capital F be a function from the positive complex plane, okay? So this means real part of Z is greater than 0, okay? Into C, okay? Since apparently we seem to be talking about complex analysis, okay? Then you can consider okay, a function f sub x of y, which is just f of x plus I y. All right, so this is the function that you get by fixing a value of the real part and considering only a function of the imaginary part. Okay, so again, these will be functions which are obtained by restricting f to these vertical lines. Okay. All right, and so then so then what you do is you can think of taking the convolution P x convolved with f x, and then P x convolved with f x, and then taking the limit as x goes to 0. Okay, and that, you know, and so you know, if f has nice properties, then we know by our properties of approximate units that, you know, maybe this thing should converge to something nice. And it's somehow what you're interested in here is you're interested in, so this converges to the boundary function for f on the imaginary axis. Okay, so I'm not being super precise here, but I'm just hinting at something here. And so the idea is you have some function f which is defined out here. Okay, and then you're going to take convolutions for fixed x, okay, as x goes to 0, and the idea is you're going to converge to something, and it should be kind of, you know, the boundary values of f, okay, as as x approaches the, or z in the complex plane approaches the imaginary axis, okay, and the mode of convergence you get there, you know, kind of matters. And so it turns out that the Poisson kernel gives you a very useful way of studying this kind of convergence of a function defined on the positive half plane to its boundary values. Okay, so there's some connections here to complex analysis is the point. Okay, good. And it just turns out that the Poisson kernel this is where the Poisson kernel sees its it's one of its most useful applications. Okay. Another kernel which will show up for us. So the Poisson kernel we're not going to see, but I did want to, we're not going to see it explicitly. It'll bloom behind certain things that we talk about when we talk about system theory, actually. But it won't show its head. It'll be kind of under the surface. And if I remember, I might make some comments about it at that time. But this kernel, which is called the Fejér kernel. All right, so you see these kernel functions now starting to appear, and so these are very important in many areas of application, but especially for Fourier analysis is where we're going to see these things. Okay. All right, so the Fejér kernel is defined like so. Again, it depends on a parameter, which I'll call capital omega. And it's defined as sine squared 2, sorry, the 2 goes on the bottom, pi omega t over, no, sorry, the 2 doesn't go on the bottom, the 2 shows up in some other kernel, which we'll see in a second. Pi squared omega squared t. Okay, and this is true as long as t is not equal to 0. And then at 0, you just use L'Hopital's rule to take the limit as omega goes to 0, and then you'll see that this thing will be continuous if you take the value at t equals 0 to be omega. Okay. All right. So Fejér kernel. So this one has some oscillatory behavior. Okay, unlike the Poisson kernel, which is, you know, kind of decays monotonically to infinity. The Fejér kernel does that in a oscillatory way, but nonetheless, the idea is very similar. Okay, so for small omega, so notice that this thing is always positive. Okay, so it oscillates, but it does so in a way that's sort of like this. Okay, and then as omega gets larger, the frequency of the oscillations also gets larger. Okay, so it gets messy here after a while, but you get the idea. Okay, I could have done that in a different color, but never been a big color person. All right, and so as omega becomes larger, you get something like this. Okay. All right, now this has lots of interesting things are sort of going on here that are interconnected in complicated ways. So first of all, its integral is indeed equal to 1. Okay, so the normalizing factor here on the bottom is designed to achieve just that. And sorry, I made an error. Okay, so it's easy to see that this is an L1 by fixing the mistake that I made, because this thing decays like 1 over t squared. Okay, but then to check that its integral is equal to not just finite, but equal to 1, that requires doing some trig integration, and you can do this by contour integration, right? So it's a if you enjoy contour integration, here it's a nice example of contour integral. Okay, and when you do this, one of the things that shows up, and you can kind of see here that there's this function kind of sine t over t that's going on here, right? And it seems to be squared, and then and the specific Fejér kernel has some constants here. Okay, but you can imagine that in trying to integrate, say, the Fejér kernel, it's useful to look in detail at the property sine t over t, and also its square. Okay, so let's think about that. So let me summarize all that as follows. To verify this, okay, one uses the function sinc, the sinc function, which is sine t over t, or t not 0, and it's 1 when t is equal to 0. So again, it's the thing that the value at 0 is just what it needs to be for that thing to be continuous. Okay. So the sinc function so the sinc function is not in L1. Okay, so unlike the Fejér kernel here, which is positive, okay, and squared, so it's really the squaring here that makes sure that this thing is in L1, because then you get that factor t squared in the denominator. Okay, that you don't have for just the sinc function. Okay, so the sinc function oscillates, but it has some negative bits to it. Okay, so the sinc function is not in L1, but it is in L2. Okay. All right, so the sinc function, it kind of it's some attenuated sine wave, okay, where its magnitude is going to 0, like 1 over t. Okay, and so this is an example of a function which is whose integral, all right, and so both of these things are true, and so this means that the integral of its absolute value, okay, so like that, is not finite. Okay, the integral of its square is finite, and additionally, it's true that the limit as capital T goes to infinity of the integral from minus t to t sinc t dt is equal to 1. Okay. All right. So so this is a nice example of a function. Oh, sorry. I knew that didn't feel right. It's pi. Okay. The point is it's finite. Okay. And so this is an example. So sync is conditionally integrable. But not absolutely integrable. Okay, and this is going to be important for us. Okay. All right. And then sync the sync squared function. Okay. Well, you know, the sync squared, if sync is in L2, then the sync squared function is in L1. And it's also in L2. Okay. So, you know, it's in L1 again, just because when you square it, it now decays to 0 at infinity to like 1 over t squared, which is enough to be integrable. And being in L2 only makes it better, because now it's going to, the integral you need to verify goes to 0, like 1 over t to the 4th. Okay. All right. So so this kernel contains inside its analysis some interesting factoids about this interesting sync function. All right. And just like the Poisson kernel, okay, you can replace essentially the omega with an integer value. Okay, and so you get that f j omega of t. Okay, so what's that? That so constants, right? Pi squared omega. Okay, so this is sine squared pi j omega t over pi squared j omega t squared. Okay, and this is so you can combine the j there with the t there, and you can put j squared there and put a j on top, and the point is you get the same formula as you do for the Poisson kernel. Okay, so this so in other words, the sequence fj is an approximate identity. Okay, so this means f with omega equals j. Okay, good. All right, so those are the kernels we're going to look at. There's other ones, lots of them, but these are the ones I'm going to talk about. Okay, so now you have also approximate identities on the positive half line. Okay, so these are going to, you know, to do with functions whose support is bounded on the left. Okay, and so in this, and so I'm going to now go through this more quickly. So the conditions for an approximate identity. So conditions on uj. So an approximate identity is still a sequence. The conditions now are we still have this. Sorry, I should say the first condition is still going to be that the UJs are in L1. Sorry, that'll be covered by the next thing I'm going to say. Okay, so I'll go back to where I was. So UJ of t dt is equal to 1. 2, there exists a positive m such that the L1 norm of these UJs is bounded uniformly in J by M. And then you have a condition about the tails, okay, just like in for the approximate identities on R. Okay, so for alpha positive, okay, the limit as J goes to infinity, interval from alpha to infinity, okay, of uj of t dt goes to 0. Sorry, equals 0. Okay, so the defining conditions are the obvious adaptation of those for right, the obvious adaptation of those for signals on R to signals on R greater than or equal to 0. Okay, so then you have approximation conditions that are more powerful by virtue of the fact that convolution has a broader domain of applicability. There's more convolvable signals on the positive half line than there are on the entire real line. So we have various conditions for approximation, and they read like this. So if F is in LP loc, okay, as opposed to LP in the on the real line, okay, so this converges to F in LP loc. Okay, so this means with the semi-norms defining the topology for LP loc. Okay, all right. Then you have the continuity conditions. And again, you get a more powerful result here than you do on the real line. So in the real line, we had 2 results, right? For continuous signals, we had these 2, okay? And we needed boundedness and uniform continuity in order to give convergence on compact subinterval or compact subsets, and then convergence, uniform convergence on all of R, okay? So in the for signals defined on the positive half line, we get a much better result. And the result is that if F is in C0, RF, then F star UJ converges to F in C0. Okay, but remember what the topology here is, okay? The topology, because these are not necessarily, sorry, both cases I need. Okay, The topologies, because continuous functions on the positive half-line are not necessarily bounded. We don't have a norm topology here. And so this isn't uniform convergence on all of the positive half-line, but it is uniform convergence from 0 to t for every t. Okay, so in this case, the mode of convergence you get is rather like a combination of what you get here. Okay, so you get uniform convergence on compact subintervals. Okay, but you do not require f itself to be uniformly continuous. All right, so it's an improvement in the way that it doesn't require uniform continuity. Okay, and examples, so I'm not going to belabor this. Okay, so take examples from approximate identities on R. And restrict to the positive half-line and multiply by 2. Okay, and you multiply by 2 in order to guarantee that. Okay. All right, more interesting for our purposes are periodic approximate identities. Okay. Okay, so what are the conditions? Okay, so I'm just going to do like I did here and just state the conditions on the sequence uj. And, you know, they're the obvious conditions. So first is that the integrals over a period, and you can make the period whatever you want. The normal, maybe the most natural thing to think about is the symmetric period about 0, rather than say the period from 0 to t. Okay, but actually, you know, for the purposes of the condition, it doesn't matter. Okay, the integral over a period should be 1. Okay, you still have this condition of uniform boundedness of the L1 norms. Okay, but keep in mind here, when I write the L1 norm, I'm writing the L1 norm of a periodic signal. Okay, so this means the L1 norm from similarly as here, minus t over 2 to t over 2, or 0 to t, or whatever period you want, but definitely not, of course, the L1 norm on all of R, because the only periodic signal whose L1 norm is over all of R is finite is the 0 signal. So, okay. And then you need a condition that, you know, sort of is analogous to this condition, and the corresponding version of that for approximate identities on R. And it reads like this. You need to have alpha positive, but not too big, of course, because we're talking about periodic things. Okay, then you have the limit as j goes to infinity interval from, and so you're integrating, you're going to take away, you're going to take the interval t over 2, t over 2, and you're going to excise the interval from minus alpha to alpha. Okay, so you're going to exclude the interval of width 2 alpha around 0. Okay, so this is the analog of the conditions in the other two cases. Okay. All right, so those are the conditions you need for an approximate identity. Okay, so again, I'm just going to sort of spit out the approximation conditions, and because the domains here are compact, again, you get an improvement of things in the C0 case. All right, so the first one is that if F is in LP per, this implies that and so when I write the convolutions here, of course, I'm talking about the periodic convolution. Okay. In the C0 case, and again, you don't need any uniform continuity conditions here. In this case, because of periodicity, so every F in C0 per is automatically uniformly continuous, because essentially you only care about the function on a compact, on a single period from minus t over 2 to t over 2, or from 0 to t, and continuous functions on compact sets are uniformly continuous always. Okay, that's what's called the Heine-Cantor theorem. All right, and then the periodic convolution. This converges to F uniformly, period. Okay. All right. All right, so and that's oh, so sorry, up yeah, I forgot one in the in this case as well. You get and so I'll just say pointwise analogous to previous case. All right, and so we had this condition, remember, up here for pointwise convergence. Okay, this one. Right, you get an analogous statement for pointwise convergence at a time where these limits exist. And I should say that on for approximate identities on the positive half line, you can the assumption is just that it's an L infinity. Okay. So sorry, I take that back. So on the positive half line, it'll be an L infinity loc. Okay. Just like here, just like here, you only need LP loc, and here you didn't need C0 bounded. You can get away with C0. Okay, so it's analogous, and the signals are an L infinity loc. Okay, so I don't want to dwell on it. I'm not that interested for what we're going to talk about in terms of Fourier analysis. It's the approximate identities on all of R and the periodic approximate identities that are most important. Okay, but in any case here, the condition for pointwise convergence is that f is in L infinity per. Okay, and that the limits, exactly as I defined before, f plus of t naught and f minus of t naught exist. Okay, then you get pointwise convergence at t naught. Okay. All right. So sort of, again, it's the examples that I kind of wanted to think about. All right. And so we'll look at the kind of same three that we talked about before. Okay. All right. All right. So and so what we're going to do is we'll look at a couple of things. What we're going to do is we're going to construct periodic approximate identities by periodification. And we talked about this a little bit last time, by a periodification of aperiodic approximate identities. Okay, and so that means I'm going to take a U and I'm going to take its periodification. And remember the formula for that. Okay, so U of t, the periodification of U at t is U, and then you take it and you shift it by all of its integer multiples of t. Okay. All right. Now, so for the Poisson kernel, you can go ahead and do that. You get some complicated formula. Okay, you can, so you get P per, okay, of T omega is going to be per T of P omega. All right. So this will get you a periodic approximate identity, right? And it's some complicated formula that you can explicitly calculate. All right. But it's most interesting when you do the analog. So remember that we talked about converting per omega of t into P of X and Y, right? So it's most interesting to think about doing that for the Poisson kernel, okay? And so the idea was you think of it as a function of two variables, and we thought of it as being a function in the complex plane. And so for the Poisson kernel, the best way to think about that is, so in this case, we thought about it as a function defined on the positive half plane. So in this case, because things are periodic in the sort of the y direction, okay, we're going to think of these as being defined on a disk. And so we're going to, instead of using x and y, we're going to use r and theta. Okay, so and here's so it's a little bit more complicated here than it is in the aperiodic case, but so replace omega and t with r and theta, and here r and theta are going to be defined by e to the minus 2 pi over omega, and then we're going to just scale theta so that it's goes from 0 to 2 pi. Okay, so it's going to be 2 pi t over t. Okay, and so you can see here that as omega goes to infinity, okay, 1 over omega goes to 0, and so this thing goes to 1, okay, and then as omega goes to 0, this goes to 0, okay. So in other words, r goes to 0 as omega goes to infinity, okay, and as omega goes to 0, this goes to 1, okay, and so the let's see, I'm not sure I said that right, so sorry, let me say it again. So as omega goes to infinity, okay, this goes to 0, and so this goes to 1. Okay, so as omega goes to infinity, r goes to 1, and then as omega goes to 0, r goes to 0. Okay, and so the point is that omega goes to infinity, which is the case that we cared about there, r is going to 1. Okay, and the point is when you make this substitution, then you get a more recognizable form of the Poisson kernel, and it's this. All right, and the role that it plays here is rather like the role for this thing in the case of the positive half plane. So in the case of the positive half plane, remember what we did was we had a function which was defined out here, and we evaluated it on the vertical lines, and then took the limit as x goes to 0. Here, we take the value of this thing, not for fixed y, but for fixed r. And then we let r go to 1. Okay, so this is r equals 1. And then inside here we have disks of other radius. Okay, and then if you have a function f from the disk in the complex plane into C, okay, so this means okay, so the unit disk, and then you're going to define FR of theta to be F of R and theta, and then you're going to take PR convolved with FR, and then you're going to study the limit as R goes to 1. Okay, and this will be, the same kind of thing. It'll be the boundary function. Okay, and so again, there's this connection with convolution and complex analysis. Okay, and so that's the importance of the periodic Poisson kernel. The exact formula for this thing isn't so important. What is important is the complex variable version of that. Okay. All right, good. Then you can talk about the periodification of the Fejér kernel and the Dirichlet kernel. Now, those formulas are more complicated, and well, they're not more complicated, but they're more interesting. And the reason is because the Dirichlet kernel and the Fejér kernel come equipped with their own, kind of frequencies, right? So. Sorry for a second. Oh, sorry. And anyway, it comes equipped with its own frequency like this. I haven't talked about, I forgot here to talk about the Dirichlet kernel. And maybe I won't in the periodic case either. I'll just talk about the Fejér kernel. We'll see the Dirichlet kernel when we talk about Fourier things later on. But let's just talk about the Fejér kernel. So we can think about this. Okay. Now there's a formula for that, and we'll give that formula. But to give that formula, first we're going to define the periodic Fejér kernel, and this is going to be sine. Sorry. 1 over, and so it's going to now depend on an integer parameter n, okay? And it's sine squared n pi t over t, when t is not an integer multiple of capital T. And then it has the value n, and again, it's the value required to make this thing continuous when t is at the integer values of t, integer multiples of t, sorry. So this is the periodic Fejér kernel. Okay. And then there's so I didn't talk about the Dirichlet kernel, as I said, but I will talk about the periodic Dirichlet kernel. And the Dirichlet kernel will come up later. Okay, so this one is sine 2n plus 1 pi t over t over, oh, sorry, I forgot the denominator here. So the denominator here is sine squared pi t over t, and here it's sine pi t over t, all right? And so this is true again for non-integer multiples of, or for times that are not integer multiples of t, and it has that integer multiples of t, the value 2n plus 1. Okay, and so the question is, what's this? Okay, well, you want it to be kind of that, right? You want the periodification of the aperiodic Fejér kernel to be the periodic Fejér kernel. Right, so this is what's called the periodic Dirichlet kernel. Now, so as I had sort of mentioned before, the problem is that the Fejér kernel has its kind of frequency, which is determined by omega. The periodic Fejér kernel has also its own frequency determined by n, okay, and t. And the two natural periods of the periodification and this thing may not be the same, and so you get a complicated interplay between the periodification of the Fejér kernel and the periodic Fejér kernel. All right, and so it's an interesting formula, so I'll write it down. it is. Okay, so okay. Right, plus 1 minus n over t. I need to tell you what n is here, but I'll do that. Right. All right. So what you see is that you get a linear combination of the Fejér kernel and the Dirichlet kernel. Okay. And the coefficient in the linear combination, you can see here that if n over t omega is equal to 1, then this goes to 0 and this becomes 1. And so in the special case where n is equal to t omega, then the periodification of the Fejér kernel is the periodic Fejér kernel up to this constant here. Okay, but I need to tell you what n is here. So where n is the smallest integer with n greater than omega t. Okay. All right, and so like I said, when n is equal to omega t, okay, so that in that case, the smallest integer greater than or equal to omega t will be exactly n. Then this goes to 1, and this goes to 0, and this goes to 1, and you get a much simpler formula. Okay. All right. And so, as I say, there's other kinds of kernels that that you can talk about. But these are the ones that are going to be interesting for us. And I wanted to kind of see how this periodification comes up here in terms of these kernels. So I wanted to make that explicit. Okay. All right. Okay, so I think I'll finish there for today, and next time we'll finish this topic of approximation and regularization, and there's a few things that we'll need to do. So we've mainly been concerned here with approximation of functions. There's also approximation of distributions, and then there's also combined with that, there's regularization. So taking something which is discontinuous, possibly, and then making it infinitely differentiable by convolution, and then combining those two things to get approximation by very regular functions. Okay, so that's where we'll get to next time.